For thousands of years, humans have looked up at the moon and wondered what secrets it hides. It has inspired myths, guided calendars, and lit the night sky for every civilization in history. Yet despite being our closest neighbor in space, the moon remains surprisingly mysterious. Even after astronauts walked on its surface during the Apollo era, much of what lies beneath the lunar dust stand, what it means for the future of exploration, is still unknown. Now, NASA is preparing to change that. In a major announcement, NASA revealed the selection of 3 new scientific investigations that will travel to the moon as part of the Artemis program and the Commercial Lunar Payload Services (CLP's) initiative. These missions will study the moon's surface terrain, internal heat, and radiation environment, helping scientists understand not only how the moon formed, but how humans can safely live and work there in the future. These payloads are expected to launch no earlier than 2028, but the knowledge they deliver could shape lunar exploration for decades to come. A new way of exploring the moon. What makes these missions especially important isn't just what they study. It's how NASA is getting them to the moon through the CLPS program. NASA works with American commercial space companies to deliver scientific instruments to the lunar surface. Instead of building and launching every mission itself, NASA relies on private industry for transportation, while focusing its own efforts on science, exploration, and long-term strategy. This approach allows NASA to send more missions, more often, and at lower cost. It also encourages innovation, supports a growing lunar economy, and creates new opportunities for science and technology development. According to NASA officials, CLPS is about building a steady pipeline of lunar exploration, one that supports scientific discovery today while laying the groundwork for human missions tomorrow. At the center of this announcement are 3 powerful scientific payloads, each designed to answer critical questions about the moon, seeing the moon in a whole new way. Amelia 3D THE first payload is called EMELIA 3D, short for Emission Imager for Lunar Infrared Analysis in 3D. While the name may sound technical, the idea behind it is simple and incredibly powerful. The moon has no atmosphere to trap heat. As a result, its surface experiences extreme temperature changes, burning hot in sunlight and freezing cold in shadow. These temperature shifts carry hidden information about the moon's surface. Amelia 3D will use a thermal imager to measure surface temperatures while a stereo pair of visible light cameras captures detailed images of the terrain. By combining these measurements, scientists can build 3-dimensional thermal models of the lunar surface. Why does this matter? Because the moon is covered in a fine, dusty layer called regolith. The way this dust heats up and cools down reveals how thick it is, how compact it is, and what lies beneath it. These details are crucial for safe landings, rover movement, and astronaut navigation with Amelia 3DS data. Mission planners can better identify stable ground, avoid hazardous areas, and choose safer routes for both robots and humans. The payload will also help engineers design equipment that can survive the moon's brutal temperature extremes, led by Dr. Andrew Ryan of the University of Arizona. EMELIA 3D will help transform the moon from a flat, distant object into a detailed, temperature-aware world we can better understand and safely explore. Digging into the moon's deep past, LISTR, while Amelia 3D studies the surface. The second payload, LISTER, looks beneath it. LISTER stands for Lunar Instrumentation for Subsurface Thermal Exploration with Rapidity, and its mission is to measure how much heat is escaping from the moon's interior. Every rocky body in the solar system has a thermal history. Heat inside a planet or moon comes from radioactive elements, leftover energy from formation, and ancient geological activity. By measuring heat flow today, scientists can reconstruct what the moon was like billions of years ago. LISTER works by drilling below the lunar surface, stopping at intervals to measure temperature changes and how efficiently the subsurface material conducts heat. These measurements reveal how much internal heat the moon still produces. A previous version of LISTER already proved its capabilities during Blue Ghost Mission 1, where it drilled about 3 feet into the moon and collected multiple temperature readings. This new investigation builds on that success, aiming to provide a clearer picture of the moon's internal structure and evolution. Led by Dr. Seiichi Nagihara of Texas Tech University, Lister's findings could answer long-standing questions. Was the moon once more geologically active? How quickly did it cool? And how did massive impacts shape its interior? Understanding the moon's thermal history also helps scientists better understand Earth's early past, since both bodies formed around the same time, facing one of the biggest challenges, radiation and SEL, and the third payload. Selene tackles one of the greatest obstacles to long-term human exploration, radiation, unlike Earth. The moon has no global magnetic field and no thick atmosphere to protect its surface. This leaves astronauts exposed to galactic cosmic rays high energy, particles that travel across the universe at nearly the speed of light. When these particles strike the lunar surface, they generate secondary radiation, including ions and neutrons that bounce back into the surrounding environment. Until now, scientists have never fully measured this radiation directly at the lunar surface. Selene, short for site-agnostic energetic lunar ion and neutron environment, will change that. For the first time, Selene will study both primary cosmic radiation and the secondary particles created when that radiation interacts with lunar soil. This data is critical for designing habitats, spacesuits, and mission schedules that keep astronauts safe. Led by Dr. Drew Turner of Johns Hopkins University, Selene will also improve space weather prediction and radiation models not just for the moon, but for other airless worlds across the solar system, turning the moon into a living laboratory together. These 3 payloads turn the moon into a living laboratory. DHOZ shows us how the surface behaves. Lister reveals what's happening below. Selene tells us what astronauts will face. Above, their combined data helps reduce uncertainty, one of the greatest risks in space exploration. For astronauts, this knowledge translates directly into safer landings, smarter planning, and longer missions. These investigations are also site-agnostic, meaning they don't need a specific landing location to be useful. NASA will assign them to future CLP's missions as opportunities arise, keeping exploration flexible and efficient, building the future of human spaceflight. These missions support the broader goals of the Artemis program, which aims not just to return humans to the moon, but to establish a sustained human presence there. Artemis is about learning how to live on another world, how to use local resources, protect human health, and prepare for even more distant destinations. The moon is the testing ground. Technologies tested through CLP's precision landings, robotic drilling, autonomous instruments are the same ones needed for Mars and beyond. The lessons learned here will guide humanity's next giant leaps. The beginning, not the end. The moon is no longer just a destination. It is becoming a stepping stone, a classroom, and a gateway to the solar system. As these Artemis payloads make their journey to the lunar surface in the coming years, they carry answers to questions humans have asked for generations and solutions to challenges we have yet to face. Quietly, patiently, the moon is teaching us how to explore the universe. And this time, we're listening.